Okay, let's start this with the concept of fluids, a topic of fluids. We are talking two things here, a static fluids and a dynamics fluids. So let's continue. The topic that we are going to discuss is what is the fluids, and then the density, and then the pressure. And then we're talking about the gauge pressure and absolute pressure, the difference between them. And then we're going to discuss some things about the measurement of pressure by means of barometers and manometers. And then we're going to discuss Pascal laws and buoyancies of Archimedes law. This is in the static fluids situation. Then afterwards, we will discuss the dynamics fluids. So it means the topics of flows and then some of the viscosity and then the Stokes theorem. So let's start with consider what is the fluid is the question. Well, fluid is a state of matter that we say that it cannot withstand this shear force. So let's talk about force first. There are two types of force. When you pull the object, stretch it out, this is called tensile force. But when you slightly apply force over it in the perpendicular to the axis, and then it's bent to the side, this is called shear force. Let's take a look at these pictures. This is what we call shear force. The object will move to the side. Okay, laser pointer doesn't work. Let's use the arrow. Now, when we say state of matter, we know that there are three states of matters. There are solid form, there are liquid form, and there are gases. Now, the difference between these three states is that I have an example here. Let's maximize it. Now, if you have a solid, for example, an ice cube, and you put it in a container, so like, for example, the glasses, the ice cube will remain the cube shape and it keep the volume as long as it doesn't melt. So in this sense, a fluid is an object that retains its shape and its volume to be, I would say, almost constant. It can change a little bit by thermal expansion and some other properties, but most likely that it is remain almost the same shape and volume. And that is the concept of solid. Now, if you give an energy to a solid by terms of thermal energy, at one point, that energy gonna break that bond or the crystal structure or whatever hold it in place, hold the molecules in place. And then the solid will underwent the what we call a transformation of state. That will happen at the constant temperatures. The molecules of the solid will become free from the crystal structure or whatever the structure it has, and result in a more free to move molecules, but still slightly attached to each other. After it completely transformed into a second state, which is a liquid state, it will start to rise up in energy again once you give, once it is completely changed the state. So the action of changing the state is called a action of transformation from one state to another. So when an object reach a liquid state, it become viable to move. So it can move or it can change the shape. So the ice cube they put in the glass, when it reach the liquid state, it will change the shape, but still the volume of it remain almost constant, or actually it will remain a little bit smaller than the solid state. Because when you are in solid state, usually a structure that is formed is going to be a little bit bigger than in liquid state. So water is a state that is denser than the solid ice. But still, the volume of it remains the same. It's not changed that much. It will not completely, will not expanding, or it will not distributing around. This is called a liquid. But then if you keep on give it energy, the temperatures of the liquid will rise, and then eventually it will reach another transformation that will be a transformation from liquid state to gaseous state. When it reaches this transformation, an energy is used to free every molecules from each other. So when it reaches gaseous state, each molecules will be completely free from each other, so it can free to move anywhere. Now, if you have a container that you fill with an object that is still changed into gaseous state, the molecules of that will be expand until it is everywhere inside the chamber. So we completely we compare these three states. We know that when it's solid state, it can keep the shape and the volume. But when it is liquid state, it can change the shape, but it still keeps the volume. But when it reach the gaseous state, it changes both shape and the volume. So it's expand to fill in the whole volume of the container. Now this is three states. Usually liquid state and gaseous state are called together a fluid. Okay, a fluid means a things that can flow. Now, for liquid state, one thing that it happens is that it is at the maximum, the minimum size of volume it can retain. So if you have a liquid and then you try to compress it to make it smaller, usually it will not move as you decide. The density of the liquid usually is constant. However, according to gases, that is expand until it fill the container. If you compress it or give it high pressure, gas state will become, the molecules can become closer together. So you can compress it to get small. So in this way, we call liquid an incompressible fluid. So it's a fluid that cannot make to be less, to become less volume. But the gas state is a compressible fluid. Okay. So fluid is both liquid and gas. Liquid is an incompressible fluid and gas is a compressible fluid. Now, there are some densities of all these objects in solid and in fluid forms. For example, we have the definition of density is the mass per unit volume. So it's mass divided by volume. And if you look at some of these common substance, you see that some are solid and some are liquids. And this is all keep their density. And some are gases, for example, air. Air at standard pressure and temperatures, 1 atmospheric pressure and 273 degrees Kelvin. The density of air is 1.29 kilograms per cubic meters. This is the one that we use at the sea level. Aluminum is 2,700 kilograms per cubic meters. This is solid. And benzene is a liquid. It is at 879 kilograms per cubic meters. Copper is 8,920. Okay. One of the most interesting object is fresh water. It's roughly 1,000 kilograms per cubic meters in terms of liquid. However, fresh water and salt water have different volume. Salt water contains some of the salt in it, so it is a little bit higher density. It is roughly 1,029 kilograms per cubic meters, a little bit denser than fresh water. However, the fresh water and salt water also have different density according to temperatures. The densest water appears at 4 degrees Celsius. So when the water freezes, is actually less dense than a 4 degrees Celsius water. So when you look into an ocean, you will see that the water at the deeper water, it will getting closer to 4 degrees Celsius. So the sea water at under the depth of the ocean is roughly at 4 degrees Celsius, where the surface water can be different. It can be, if it's a polar, an Arctic water, Arctic Ocean, the surface roughly sometimes is 0 degrees or a little bit lower than 4 degrees. But if it's in the tropics, the surface water can be warm as 17 or 20 Celsius. But then as it goes deeper, it will getting colder and colder, and then eventually it reach 4 degrees Celsius. So at depth, the water is at 4 degrees, and that is the highest density of water. So roughly speaking, fresh water is around 1,000 kilograms per cubic meters. Glycerin is 1,260. Gold, a solid form, is 19.3 or 10,900. No, this is 19,300 okay, kilograms per cubic meters. Helium gas and hydrogen gas is lighter than air, so it is less than 1 kilograms per cubic meters density at standard pressure and temperatures. This is important. We have, okay, seawater is on the right side. We have oxygen gas at 1.43, a little bit denser than air because air is only 20% oxygen. Most of air is nitrogen. Mercury, which is the densest object that we have now, is well, 13,600 kilograms per cubic meters. Okay. This is a density. Now, another thing is a pressure. When you are inside a fluid will apply a pressure on, is a weight of that fluid will apply the pressure on the surface. It doesn't care which direction that your surface is on. It will eventually force a force on it. And Torricelli learned this by, well, using a containers and then pump out of the air inside. And it's turned out that the pressure of the air compress it. Okay. So a unit of pressure is force per unit area. And the unit of force is 1 newtons, and then unit area is square meters. So a pressure unit is newtons per square meters, in which we call Pascal. Now, according to a pressure by atmospheric pressure, Torricelli can prove that if you have a complete vacuum on the inside of the vertical tube of mercury, an atmospheric pressure can push mercury up by 760 millimeters. So that is called 760 torr. Given the density of the mercury, the atmospheric pressure can be calculated to be 1.013 times 10 to the 5th Pascal. Okay, or 1013 hectopascal. Hectopascal means 100 Pascal. You will see that in a weather forecast. So in unit of Pascal, a atmospheric pressure is 101.325 hectopascal, kilopascal. And atmospheric pressure is 1 in millimeters of mercury, or torr is 760. Inch of mercury is 29.92. You will see this in when you filling the flat tire. Usually in pound per square inch. Okay, here torr is 760. And how do we measure an atmospheric pressure? Pascal using a closed tube filled with mercury, and then flip it over into a mercury bath. So a mercury drop down in the tube, drop down and making a complete vacuum on top. And he realized that the mercury inside of the tube is 760 millimeters higher than the outside. So he made a summary that the pressure is pushing on one side, and then the mercury from the inside, which is lack of atmospheric pressure, is higher by 760 millimeters. So because the force must equal to the weight as it's stable. So on the outside, the pressure times the cross-section area of the tube is the force that pushed the object up. And the weight of the mercury column is density of mercury times G times the volume, which is H times A. So the A and the A cancel. So the atmospheric pressure can be measured indirectly by this, by the density of the mercury times the gravities, and H is the height. Plug in the density, which is 13,600 kilograms per cubic meters, and then H is 760 millimeters or 0.76 meters. And the gravity is, let's give you more details numbers, is 9.80665 at 0 degrees Celsius. Multiply them all, and then you see that the atmospheric pressure is 1.13 times 10 to the 5th newtons per meter squares. And sometimes they use it 1013 hectopascal, or sometimes using a unit of millibar, of bar or millibar. Okay, this is millibar, where 1 millibar is 100 pascal or 1 hectopascal. So this is an experiment by Torricelli of this pressure. Now, okay. Okay, continue the hydrostatic pressure. If you are under the surface of a liquid, or actually it's going to apply to a gas. So if we have a point of reference point to be a y over 0, and then you are deep under it by a distance of y1, and the other one is a distance of y2. Now, the weight of the fluid will push down to that point, and then it's actually expand on the side, and it's a normal force up. So the difference in pressure between level Y1 and level Y2 is the weight of the fluid in between. So the weight of the whole things from reference point to Y2 is pushing down on the layer of fluid below, and that will express the pressure back up to be P2, where the weight of the fluid from surface to Y1 is pushing on to this material. So this slab of fluid, which is thickness of Y1, Y2 minus Y1, and the surface area of A, will experience a force on the top side by P1 times A, and force on the bottom side by P2 times A. And because it have to be at stationaries or at stable, the downward force will be the P1 plus W, and the low upward force will be P2. So we have the P1A plus P at point A or point 1, plus the weight of the water columns equal to P2A's. So P1A plus rho times the volume, which is A times Y1 minus Y2, equal to and G is equal to P2A. Or Y is the thickness of Y1 minus Y2 is Y. So we got P2, it depends. This is different. This is usually at Y1 and 0. Sorry about that. So downward force at the depth of P1 is the weight of the whole water column plus the atmospheric pressure. So the atmospheric pressure times A plus the weight of water column equal to P1 times A. And PA is the pressure, atmospheric pressure times A plus rho Y1G plus equal to P1 times A. And the pressure at depth Y1 is PA plus rho GY1. Or you can also say that the difference in P1, P2 minus P1 is rho G Y2 minus Y1. And we call the pressure at that depth an absolute pressure. And then it has because the air have atmospheric pressure at the surface, so we still have atmospheric pressure everywhere. And then there's a difference between the pressure at the surface and the pressure at the depth. This is called a gauge pressure. And the gauge pressure is, by definition, the difference between the absolute pressure at that depth subtract by atmospheric pressure. And it is rho GY. Okay. And Y is the depth of the fluid. So because in everyday life we all live in the atmospheric pressure, so the pressure that we measure is actually a gauge pressure in everyday life, because when we measuring the pressure, we use a difference between the atmospheric pressure and the pressure inside. Okay, get back here. How can we measure the difference in temperatures? We use the concept that the pressure at the same level are equal, and this is called Pascal law. So if you have a U-shaped tube, and then U-shaped tube, and then you pull in the fluid. For example, it can be water or some kind of heavier, maybe sometimes mercury. And this system is called manometer. So as long as the pressure on the left and the right are equal, the level of fluid inside the tube, it will be equal on the left and on the right. However, if you plug it into something that have higher pressure, so this is called a gas, plug it to a tank of gas with the absolute pressure PGs. The pressure on the left will push the level of the fluid down, and the imbalance on pressure will causing the column of fluid on the right to rise up. And because at the same level, the pressure will be the same, so the pressure on the gas will be equal to the pressure on the atmosphere plus the height of this pressure. And we see that PG is rho GH plus PA. So the pressure on the right is equal to and this is called the gauge pressure. So when we do measuring this, what we read is the gauge pressure. So in the absolute pressure, you have to add PAs inside. Now, what happens if one side having another type of fluid, which is different density? For example, you put oil on one side and then there is water on the left side. Now the weight of the oil will create pressure, which is gauge pressure. We will neglect the atmospheric pressure on the left and on the right because it will cancel out. If we can continue to add it up, but it will cancel out at the end. So the gauge pressure from the oil is rho oil times G times H, the height of the oil to the surface. And then on the other side, the water column is rise up, okay, by the distance L. So the density of water times G times L will equal to the pressure by the oil, because if we use this as a reference point, the pressure on the left and the right must be equal. So rho G L plus D, well, we have to add atmospheric pressure by this column, equal to rho of oil times G times H, H is L plus D, equal to rho of water times G times L, and then we neglect the density of air. So rho of oil times G times H equal to rho GL, and we have that density comparing to water is density of oil compared to water is the height of the column of oil divided by the column of water, or column of water divided by column of oil. Now, in this case, oil must be less dense than water to be float on top. So it turned out to be that L must be always smaller than H. Okay. Let's look at some examples on the manometers. The thing we see most in manometers is when you're doing a blood pressure test. A blood pressure test, you push the air inside the bag of that is wrapped around your arms. And when the pressure inside the bag is higher than the pressure in your blood vessel, it will compress the blood vessel such that the blood cannot flow. Now, there is a voice sensor inside that bag, or before it was invented, the doctor had to use a stethoscope and listen to the voice. Now then, after the vessel is completely stressed, well, maybe the pressure on the outside will reach around 200 millimeters of mercury. And then the valve is released, the pressure will going down. When the blood pressure of the blood is equal to the pressure of the bag, the blood will start to flow through the vessel again. And then the doctor will hear a hissing sound of the blood going through. Then he will look at the levels and then mark it as what we call a systolic pressure. At the highest point of the pressure inside the blood vessel is when the heart compresses. And after a systolic pressure reach, you will feel the pulse in your arm until the pressure of the bag reach the lowest pressure inside the blood vessel. This is called a diastolic pressure. And the diastolic pressure is when the heart relaxes. So as long as your heart is functioning properly, the difference between there must be a difference between systolic pressure and diastolic pressure. Now, in some condition, well, death due to heart failure, it have two things. It can happen when the heart completely relax and they cannot pump the blood or it cannot increase the pressure. In that case, the systolic pressure will equal to diastolic pressure. Now, on the other hand, the muscle may be failure to compress, and then, oh no. On the other hand, sometimes the heart is spasm, so it's compressed and then it's not relaxed, not relaxed. Okay, in that case, the diastolic is increased up to the systolic. So there are two ways of death in terms of the heart. Now, this is because the manometer is used comparing to the air pressure. This is called the gauge pressure. Okay. Now, if you want the absolute pressure, the pressure that the heart can be pumped is you have to add 760 millimeters of mercury inside into. So how much is 120 millimeters of mercury? So it can pump mercury up by 120 millimeters. So mercury is 13.6 times denser than normal blood or water. So compare it to the actual blood, you have to multiply 0.12 meters to a 13.6 times higher. So for a normal blood, the heart can pump it higher by 1.6 meters. So you multiply 120 millimeters by 13.6 times. Okay, to be a water or let's say blood is roughly the same density of water. It can pump the blood by 1.6. Okay. So let's take another example. This is a little bit political. A Royal Thai Navy, we know that the Navy is buying a submarine from China. It's called a Yuan class. And it's a special Yuan class. It's a Yuan class that reduce the scale to fit the depth of our Gulf of Siam. It's operate at a depth of 50 meters from sea level. Why is this operate at this level? Because the Gulf of Thailand depth on average is around 70 meters. So if it operate deeper than this level, it will stuck in the mud. So at least what happened is that even at this 50 meters from sea level, find the force that acting on the submarine hatch, assuming that it has a 1 meters area at that depth. So in order to get in and out of the submarine, you have to go out and in to the hatch. The hatch is the door that closer actually from the outside, because when you get inside the submarine, the pressure is pushing inward, and inside has lower pressure than the outside. So at 50 meters depth, the gauge pressure at that level is rho GH. So it is the density of the seawater times G times CH is the depth. So it's 1,030 kilograms per cubic meters times 9.8 meters per second square. We should have a square here. And then a depth of 50 meters. And it gave you 5.05 times 10 to the 5 Pascal, or 505,000 newtons per square meters, 505,000 newtons per square meters. So it's roughly 4.98 atmospheric pressure. Divide this by 1.13. And this is equivalent to 51.5 tons of weight. Okay, so you cancel, you divide by 10 to give you a weight in kilograms. You divide by 1,000 to give you a weight in tons. So one square meters at 50 meter depth, having a force on equal to the weight of 51 tons. So once a submarine submerged by more than a few meters, it will be unable to open that hatch. And actually, a human body can withstand the pressure only when you are less than 30 meters depth, or less higher than not higher than 4 atmosphere. So that's the reason sometimes they calling a submarine is a diving coffin. If you're going down to the sea floor, which is higher than you can actually get out. Sometimes the submarine has a system that flooding. There is a stories of a sailors in World War II that survived the sunken submarine by put themselves into a torpedo tube and then flood the tube so that the pressure inside and outside are equal, and then they're going out. But they have to have someone on the inside to help them closing the tube and flooding the tube. But that will work only when you are at near the surface, because your human body cannot withstand that height. So right now they have a rescue submarine. It is another submarine, another small submarine that have a vacuum hatch. So they have a temporary hatch that will attach to a surface of another submarine and then pump the water off. So the people, you can open the hatch and then climb up to another a rescue submarine, and then you close the hatch and remove it, and then going out. But then the rescue submarine is only a few countries have that kind of submarine. Okay, so this is a reason that, well, there are many accidents in the submarine that people cannot escape. Let's take another example on the dam or a water side of the wall. So in 2012, there is a great flood in Thailand. And sometimes, well, the system to prevent flood in Bangkok is a series of what we call a water resistant wall and a gate, a water gate. So it's actually a steel plate that closes between the two walls on the outside. Now, when this gate closes, the level of water inside and outside are different. So because the level of water that are different, there is a force acting on this wall. But the force is not constant because the deeper the water, the higher the force. So at the bottom of the canals or of the gate, the pressure is rho GH, and the pressure at the top of the surface of the water is 0. So the average pressure on this is rho GH over 2. We can use this because the pressure is increased linearly. If it's not linear, then you have to do an integral. But, well, in this case, it is actually linear. So we have rho GH over 2. Now, force on the dam is a pressure average times the area. So it's rho GH over 2 times the length of the dams and the height, the depth of the water, so which is also the H. So the force on this is 1/2 rho GL H squared. So the force per unit length of the dam is proportional to the height of the water, the difference in height square. So for L equal to 1 and the density of water is 1,000 kilograms per square meter per cubic meters, and G is roughly 10, we will see that for 1 meter difference, the force is 5,000 newtons or half a ton. For 2 meters, it is 20,000 newtons, okay, or about 2 tons. And for 3 meters, it is 90,000 newtons, or it would say 9 tons. So the higher the level of water on the outside and on the inside, the higher the force. And eventually, that is too much for the dam to hold. So in that case, we have a collapsed dam, and then the water is spilled out. And it happens on 2012 at Rangsit. Okay, that's another example on this. Okay นี่ครับเรื่องต่อไปคือเรื่องของกฎของปาสคาลนะครับจริงๆกฎของปาสคาลเมื่อกี้ได้พูดไปแล้วหลักการของกฎของปาสคาลก็คือว่าในระบบทั่วไปเนี่ยความดันที่ระดับsorry let's get back to this is a Pascal law usually in Pascal law the pressure at the same level is equal. So if you have the same level, no matter how different the size and the shape of the pressure, the system, the pressure on the left and on the right at the same level are equal. So we use this to create a machine that help us lift a heavy object. For example, because the pressure are equal, we have 2 cylinders. One is the small cylinders and one is the large cylinders. And the small cylinders, the area of the cylinders is AI, and the large cylinders is A0. Now, if you press the small cylinder with the force Fi, And because this is a oil, which is an incompressible fluid, it means that the oil cannot change its volume. So once you compress on the left side down, the level on the right side will going up. So in that case, pressure are the same. So Fi over Ai is equal to F0, Fo over Ao. So the force on the bigger side, on the right side, is to be the ratio of the area A0 to Ai and times the Fi. Now, if we making our system such that the A0 is larger than Ai by, let's say, 10 times, it means that the force that this cylinder is pushing up is also 10 times larger. Okay. However, the difference is that if you push down on the left with di, the work done is still conserved. So Fi times di is F0 times d0. So instead of it moving up by the same distance, it is a lot less. For example, if the pressure and the area is 10 times, the distance that is moved up is also 1/10 of the one that push on. So even though we can using the force to lift up heavy object, but then you have to do a lot of work to do that. And this is the model for a what it calls the lifting, the power lift on the at the garage, or usually you have some of it inside of your car. Okay. Now we get into the concept of buoyancy. Because everything have a force, when you submerge an object under the water, there is a pressure on every side of the object. Now this pressure will cancel each other out, but it's not all, because the depth of the object is not equal. So at the end, there is a net force on an object that that submerged into the water. And this force is called the buoyant force. And it's always point upward. And the buoyant force is equal to the weight of the fluid that is displaced. So the buoyant force is the density of the fluid times the volume that it was displaced times g. Now, if the object is completely submerged, the submersion volume will be equal to the volume of the object. However, if the object is light, it might not submerge all the way until the buoyant force reaches the weight of the object. In that case, the object will be float, and part of it is submerged, not all of them. So there are different between totally submerged and partially submerged. Let's take a look at for an object that totally submerged. For an object with density ρ0 and the volume is V0, the weight of the object is mg, is ρ0 times V0 times g, and the buoyant force is the density of the fluid times V that is totally submerged and g. So if ρ0 is greater than the fluid, so if the object have higher density than the fluid, so the weight is totally bigger than the buoyant force, even though the object is fully submerged. So the force that actually act on the object is the difference between the weight and the buoyant force. So force is rho 0 minus rho F times V0 times G, and this object is sink. However, this is some of the advantage, because when you are submerged into a fluid, actually your weight is reduced down by the buoyant force, because this F is actually what left of your weight when you are inside the submerged in the fluid. For example, the water density is around 1,000 kilograms per cubic meters, and our body have an average density around 1,100. So it's about 100 kilograms per cubic meters different between the density of water and density of our body. So what happens when we have the same volume and when we submerge into the water? Actually, the force that our body press on the ground inside the water is reduced by 10 times. So instead of you weight 1,000 newtons or 100 kilograms on the ground, when you're in the water, you only weight 100 newtons or around 10 kilograms on the ground in water. So this is the beneficial for heavy or large animals to adapt to their environment. You see that if we see that the large animals is in the sea, because they use that buoyant force to help reduce their weight, such that their muscle can work properly. And if you drag it up to the ground, outside of the water, their body weight will be too heavy for the muscle to move. So that a disadvantage of this buoyancy force. Now, if the object are less dense than the fluid, the object will partially submerge, and until the buoyant force is equal to the weight, then afterwards the object will stop falling and it will float. So in this case, the density of object is rho 0, and the total volume of the object is V0 and G, will equal to the buoyancy, which is the density of water of the fluid, times the volume that it is submerged, which is not the same as the volume of the object, times G. So the submerging volume compared to the actual volume is rho 0 by rho F. The perfect example of this is ice or the iceberg. For an iceberg on ice, as I told you, it was a solid. So each molecules of water making a structure pattern that is fixed. And this structure pattern is less dense than liquid water. So the ice have an average density around 917 kilograms per cubic meters, and water having a average density around 1,000 kilograms per cubic meters. I think that I wrote it too quick last time. It's T3 here. So the volume of the submerged divided by the volume of the ice is 917 divided by 1,000. So it's submerged by 91.7%. So an iceberg, when you see an iceberg, actually underneath there is some things that there is ice that is pretty big under the surface of water, and only about 8.3% is above the sea of the level of the sea. And that is the disaster for Titanic, because they see the iceberg, but they don't know that there are a lot of ice, of solid ice underneath the surface, and it's scraped on the side of the Titanic, making the water spill in. And the another reason for catastrophe is that of metallurgy. At that time, it's around 1900s, early 1900s. The knowledge of metallurgy is not good enough. So they found out that the metal that used to make a Titanic hull is brittle when cold. So at that day, the temperatures dropped down to almost 4 degrees Celsius, and the metal is freeze, and then it's cold. So it become more brittle than usual. So when collide with the iceberg, it making the rivet to break out and causing a scrape to the side that causing the Titanic to sink. So that's another story relating to this. Now let's look at another example. A frog in a hemispherical pot just float without sinking into the sea of blue-green ooze with density of 1.35 gram per cubic centimeters. So it's not water, it's just something blue-green, and it's denser than water. If the pot have radius of 6 centimeters and a negligible mass, what is the mass of the frog? So we don't have a mass of the pot. But then the frog in the pot is submerged by, they say that it is a semi-spherical pot. So it's submerged by a hemisphere, a half a sphere. And the density of the fluid is 1.35 gram per cubic centimeters, and the radius of 6 centimeters. So in order for it to float like a chip, the buoyancy must be equal to mass of the frog times g plus mass of the pot times g's. And where we assume that the mass of the pot is negligible, so we cut it off. So the buoyancy is the mass of the frog equal to the weight of the frog. Now the buoyancy is the density of the fluid times the volume that is submerged times g. And because it's equal to mass of the frogs and g is g cancel. And because the pot is hemispherical, the submerged volume is 1/2 of the spherical volume, or 4/3 pi r cubed. So we have mass of the frog is density of fluid times 2/3 of pi r cubed. And because it is in gram per centimeters and density cubic centimeters, so I use centimeters in terms of radius. So mass of the frog is 1.35 times 2/3 of pi times 6 to the cube, and it is 610.73 grams, or roughly 611 grams. So this is a concept of, not usually it's a concept of boat. For a boat, if you are submerged into the water, causing the buoyancy larger than the mass of the boat, then the boat is the boat is float. So the idea is to make the boat hollow on the inside and having a larger volume. Okay. not condensed, but it's larger volume until the average density of the boat is lesser than the average density of the water. And when that happens, the boat will float. Okay, the larger the difference, the higher the mass that each boat can carry. So when you have the boat and you put in on the weight, it will help until the weight, making the average density of the boat with the cargo, making the average density equal to the density of the fluid, then it will become sink. So as long as your cargo is not too heavy, such that the volume is the density is the same as the water, then the boat will float, and well, you can manage it to going anywhere. Okay, let's take a look at another example of a submerged object. A piece of aluminum with mass 1 kilograms and density 2,700 kilograms per cubic meters is suspended from a string and then completely immersed in a container of water. So it's a picture of P1425. And then they said calculate the tension in the spring before and after the metal is immersed. Well, before it's immersed, the tension in the spring is equal to the weight of the object. So object mass is 1 kilograms, and therefore the weight is 9.8 newtons, and the tension is 9.8 newtons. Now it has the mass of 1 kilograms that have density of 2,700 kilograms per cubic meters. So the density of the object is the mass per unit volume. So it's 1 kilogram divided by 2. The volume is mass divided by density. So it's 1 kilograms divided by 2,700 kilograms per cubic meters. Kilograms, kilogram cancel, and then you get 3.7 times 10 to minus 4 cubic meters. So it's roughly around less than a liter, because 1 cubic meters is 1,000 liters. Okay, so that is 0.37 liters, or around 370 cc cubic centimeters. So after you submerge it into the water, you see, object is 2,700 kilograms per cubic meters. It is denser than water, so it's sunk. So when you completely submerge it in water, now the tension is helped by the buoyancy force. Tension plus buoyancy is mg. So tension in the string is mg minus b. So it's reduced the tension. So the tension is 1 kilograms times G minus by rows of water times submerging volume times G. And it is T equal to 1 minus 1,000 times volume is 1 over 2,700. And then the whole thing is times G. And this is 0.370. So 1 minus 0.37 is 0.629, and times 9.8. The tension is 6.17 newtons. About 1/3 is reduced. So when you are in the water, that advantage is helping you in carrying things up away around. So I have two examples, not example, to homework for you to do. This is also a Titanic. but they use a styrofoam slab instead. Remember in Titanic at the end, Rose and Jack catching a door. Okay. And then when Rose going up to the door, it can float. But when Jack tried to climb on it, it sunk. And the reason is that with the weight of the door itself, plus the weight of Rose, is not too much for the object, is not too much for the buoyancy to compensate. So the weight of Jack plus Rose is larger than the buoyancy that the door can give. So you only have, you don't have a chance for one person. Because a lot of people talking about that, you say that the door is big enough for two people to climb on and sit on it. Yes, it's big enough, but it's not buoyant enough for people to stay. And why is it not buoyant enough? Somebody is looking at it and he said that according to Titanic's plan, the door to Titanic is made from 3 different type of woods. One is the oak, one is the teak, and one is the pine. Now, out of the 3, the oak is the most dense door. It's expensive. It's used in the first class cabin. The teak is, the teak is the most dense. And then the oak, which is the less dense, but using in common area. Now, the lower level or the lower class deck using a pine door, which is the lightest one. So it turned out that they can identify the door type because the teak is too heavy that even with Rose, it cannot have enough buoyant force to support even one person. But the oak is enough for one person. But if they lucky, they got the pine door. The pine door density is enough to support 2 people. So it is lucky for Rose, but not lucky for Jack that the door is an oak one. So during the Great Flood in Thailand, a lot of people using this, a styrofoam slab. I see someone even use it for a car. Okay. It has a thickness H and density of rho S. When a swimmer of mass m is resting on it, the slab floats in fresh water with its top at the same level as the water surface. So find the area of the slab. So in this case, it has a density of the slab. The buoyancy must equal to the weight of the slab itself plus the weight of the man, of the swimmer. So you have rho density of the water, V is the volume of the slab, and then G is equal to mass of the slab. So it's the density of the styrofoam times volume times G's plus mg's. So you rearrange the term and get the answer. Another question is, okay, this is the one that we worked before. So let us conclude the hydrostatic at this moment, and we will get back to the hydrodynamics later.